Okay, in this discussion we're going to talk about the conceptual aspects of solutions. Solutions are homogeneous mixtures. They are intermingled at the molecular level. And so what we're going to talk about is the interactions between the particles, molecules, ions, and the energy changes that occur when these interactions occur. Okay, just reviewing a couple of terms. The solute is the thing that's being dissolved, and the solvent is the thing that's doing the dissolving. Okay, the first two steps, it's kind of a three-step process is how we're breaking this up. And the first two steps basically involve the spreading apart of our solute and solvent molecules, or ions, depending on the nature of our solute. And in order for them to intermingle, we have to first kind of spread them apart. And this spreading apart or expanding is an endothermic process. We have to apply energy to our system for this to occur. The types of forces that might be present in our solute or solvent could be, if the solute is ionic, then we have ions attracted to ions. We could have hydrogen bonding, especially in our solvent. If the solvent is water, for example, we've got hydrogen bonding that we're counteracting. Polar solutes, polar solvents would be dipoles attracted to dipoles. And then nonpolar solutes or solvents would have London dispersion forces. Okay, in the third step, where we have the intermingling of the solute and solvent, after they've spread apart and have space to kind of interact with each other, then they're going to be attracted together. And this coming together of the solute and solvent particles is an exothermic process. Energy is released because they are reacting to their mutual attraction for each other. Okay, and the sort of attractive interactions that we might see are ion dipole. This is where we have maybe an ionic solute that's attracted to the dipoles in a polar solvent. It could be dipole-dipole, polar solute, polar solvent. That would be like maybe sugar in water, for example. And then London dispersion, where we have nonpolar solvents, nonpolar solutes. Okay, here in this diagram, we just see some particle level pictures of what's happening in the solution formation. So just to kind of give you a little visual here. And we're going to look at an animated visual here. And the example that we have is water dissolving an ionic salt. In this case, it's I think the specific example they were using is water dissolving sodium chloride. But here we have water, our polar solvent, and so it has positive and negative sides of the molecule that can be attracted to the positive and negative cations in our salt. So here, this slide is just basically giving you a verbal description of what we're going to see when we look at these animations. And the animations are going to be divided three ways. One is just the overall process, and then we're going to look specifically at the interactions between the solute and solvent. So this first slide here we have, this is our salt crystal here in the center, the blue and gray. And then we have our water molecules, the red oxygen, the white hydrogens surrounding it. And you'll see them, they'll kind of come in and surround one of the ions and then pull it away from the solid. Okay, so this is our dissolving process. And so our solution consists of these ions of our solute surrounded by the water molecules here. And so once we have a solution, you'll see we have this intermingling at the particle level here. Okay. All right, so now let's look specifically at the attractions. Here for the cations, these gray ions here on our crystal, the cations are going to be attracted to the negative oxygen atoms in the water molecule. So you'll see as the water molecules approach one of the cations, they orient themselves so that the negative oxygen is coming up towards the positive cation. And then that way they're able to surround it and pull it away from the crystal structure. Okay, and now what we're going to see is the water molecules, the positive hydrogen is going to come in, orient themselves towards the negative ion, okay, and surround it and pull it away from the structure. So now we're getting our anion and then pull it away again. Okay, one of the basic principles that you need to remember is like dissolves like. And you've probably heard this phrase before and maybe not understood exactly what it means. But basically, it means that polar solvents will dissolve polar solutes. That in order for something to dissolve in something else, they have to be very similar in their intermolecular interactions. So let's take a look at how this is going to affect our solution formation. Okay, so here we are. This is just a slide, again, summarizing what's happening. Okay, and so the thing to think about when you're thinking about how solutions form, here we want to look at what's the magnitude of these enthalpies going to be. The enthalpy of each of these steps, is it going to be large or small? And that's pretty much at this point as quantitative as we're going to get. If the solvent interactions are weak, then we might have a small enthalpy, the delta H1. If our solute interactions are strong, then delta H2 might be really large. If we have strong solute-solvent interactions, then our delta H3 could be large. And so what we want to look at is how does the size of these affect, and how does that affect this phrase, like dissolves like? What does that mean? Why do they need to be alike in order to dissolve? Well, here's kind of a visualization. This is our vertical axis here is enthalpy. Okay, so positive is endothermic, then coming down would be our exothermics. So here, if we look at, we have an endothermic separating the solvent, separating the solute, and then when we get an exothermic for the solvent-solute particles mixing. And so what we're looking for, in order for something to dissolve in something else, the amount of energy that it requires for the separation of the solute and solvent has to be about the same as the energy that is released when they interact. Now, it doesn't have to be exactly equal. Okay, if they're exactly equal or really, really close, then pretty much we're going to not have much of an enthalpy change by virtue of mixing this or making up this solution. Okay, and to think about it from an observation standpoint, when you mix the two things together, you really wouldn't notice a temperature change. Okay, whereas some things where the energy that I have to put in is more than the energy that is released when the solution forms, then it's going to be endothermic, and we would notice a drop in temperature when we form the solution. And then conversely, if I get a lot more energy out, we have really strong interactions between the solute and solvent, then I'm going to have an exothermic reaction. It's going to release more energy than is required for the initial separation of the solute and solvent. And so again, the key thing here to remember is that in order for the solution to form, the energy that I put in, delta H1 plus delta H2, has to be close to delta H3. Okay, and so here's a couple of definitions here. We have an ideal solution if the delta H of the solution is 0, and if the intermolecular forces between solute and solvent are stronger, then we're going to have an exothermic formation of solution. And if the solute and solvent molecules are weaker, then we're going to have an endothermic delta H of solution. Okay, and so here's the key thing about where we would not have solution formation. If the forces between solute and solvent are much weaker than the other intermolecular forces, it will not dissolve. In other words, there would not be near enough energy released by the solute-solvent interactions to compensate for the energy it requires to separate the particles. A really good example of this would be dissolving salt in a nonpolar solvent like gasoline, for example. It takes a little bit of energy to separate out the constituents of the gasoline, and say we would just say octane maybe. Okay, London dispersion forces, nonpolar molecules, and so low on the energy scale of how much energy to separate them as compared to the energy that would be required to separate the ions in the ionic sodium chloride crystal. And so the interactions between the ions and the nonpolar solutes are not going to be very strong. And so when they do intermingle, we just would not gain enough energy back to compensate for the high amount of energy, relatively speaking, that it takes to separate the ions of our salt. So that's why we would not get a formation of a solution for nonpolar solvents like gasoline, for example, and an ionic solute like sodium chloride. Okay, and this is just another slide with an example. So here we have carbon tetrachloride solute in benzene would dissolve. Nonpolar solute, nonpolar solvent. Okay, polar molecules. So here we have ethanol in water. All right, so we have polar, and not only that, we've got some hydrogen bonding going on there. So we would expect it to be soluble. And then ionic compounds, because they have positive and negative ions, can interact with polar solvents as well. Okay, so here would be a type of problem, conceptual type problem that you might see related to this. Here we have 3 substances, and it wants us to rank them in order of their solubility in water. So let's look at these here. Okay, so here we have butane, dimethyl ether, ethanol, and methanol. And so our solvent that we're looking at is water. Okay, so it's polar and it has hydrogen bonding. So the more that these solutes are like water, the more soluble that they would be. So if we look at these, now we do have, so we'll kind of go from most soluble to least. Even though it says increasing, we would just reverse the order. But if we look at that, okay, here we have the methanol and the ethanol. We know we're both going to have, okay, we have polar and hydrogen bonding. All right, so both of these have a lot like water. Well, if we have 2 that are kind of like this, then the next thing we're going to look at is the relative size of the molecules. The closer they are in size, the more soluble they're going to be. So we would expect that this one, the methanol, would be the most soluble. Okay, and then this would be next. here, the ethanol. Now, let's look at the two remaining ones. This one, we're definitely going to have just London dispersion here. Here we're going to have London dispersion, but we have this oxygen in the middle of this ether here. And so we've got kind of a place here where we can get some interaction between the hydrogens, these positive hydrogens on the water, and these negative lone pairs on the oxygen there. And so the fact that we've got this oxygen here that's similar to our oxygen on our water is going to make this one, the ether, a little more soluble than the butane would be, because it's just a nonpolar. So if we were going to rank these in order of increasing, so that'd be least soluble to most, then we would have this one would be the least, the ether would be next, then our ethanol, and then the most soluble would be our methanol.